So, welcome to today's colloquium. Today's colloquium will be given by Zdeněk Dvořák. Zdeněk Dvořák finished his PhD study in year 2007 at Charles University in Prague. He was a postdoc at Georgia Tech, at Simon Fraser University, and last fall he was awarded the European Prize in Combinatorics. So, and he will be speaking about separators in graphs.
Yeah, thank you for the introduction. I actually forgot what the title of my talk is, so I couldn't write it on the board. Something about separators, and it's mostly based on joint work with Sergey Norin from McGill. So, okay, what I will be interested about are the small separators in some graphs. So, and the intuition that you maybe should have is that if you, let's say, imagine a planar graph which looks like this, let's say like a grid, then you can split it in half by, let's say, removing one of its columns. So deleting these vertices splits the graph into two parts of roughly the same size, and we only needed to remove something like square root of the total number of vertices to achieve that. And it turns out that this is not a coincidence. It turns out that this is true for every planar graph. There is a result of Lipton and Tarjan from 70s. That tells you that if G is planar, then it has a balanced separator of all the roughly square root of the number of vertices. And I should probably tell you some definitions. So what do I mean by a balanced separator? Well, a separator in a graph is a way to partition the graph into two subgraphs, A and B, such that they are, well, in our case, we will be interested in the cases where the intersection, the separation is small, and the separation is balanced if each of these parts contains only a small fraction of the vertices of the graph. Let's say the standard thing is like right there, 2/3 of the vertices of the graph. So we want that G is union of these two parts. We want that, let's say like this part has size at most 2/3 of n, and this part has size at most 2/3 of n, and then the order of the separation is the size of the intersection. So why here 2/3 and not some other constant? Well, it basically doesn't matter. You could if you are not satisfied with 2/3 but want something better, you can find separators in these smaller parts that will split things more, and then you can divide the parts more evenly. So so you can get here as close to 1/2 as you need. 2/3 is kind of the number that appears natural in some context. Let's say in the context of 3-bits and so on. So that's why people usually define it this way. And why is this interesting? Well, it's a nice property, but it also has many applications, especially in the design of algorithms. Because if you now want to make some algorithm that computes something for planar graphs, this gives you a natural divide and conquer idea how to do it. You find this small separator, you compute something for the two small parts, and then somehow combine the information together, and you obtain the solution for the whole graph. And to make things more concrete, let me show you let's say an example how we could compute the size of the largest independent set in a planar graph. Well, you find this partition, then you will guess how the largest independent set looks on the intersection, and then in each of the parts you remove these vertices that you put to the independent set and remove their neighborhoods. Find recursively the size of the largest independent set here and the size of the largest independent set here, and combine things together, and you will get the largest independent set in your graph G. But of course, only if you actually guessed correctly what the intersection of your largest independent set will be with the separation. And of course, unless you are a magician, you cannot easily guess it, so you will have to just try all the possibilities. And because the size of the intersection is roughly square root of n, you will need to test like constant to the square root of n possible choices of the independent set in this part. And so now from the recursion to compute the size of the largest independent set in G, you will need to compute the largest independent set in this many branches, and in each of the branches you will have at most 2/3 of n, 2/3 of the number of vertices you had originally. So you get this recurrence for the time complexity of your algorithm, and then you can unwind more. So here this is the same here. So c to the square root of n times c to the square root of 2/3 of n, and so forth. So after you fully recurse, you will have here some product of things which decrease geometrically. So this is the same as square root of n plus n. And so on. And so this is just this is just geometric series which sums up to some constant. So you get some constant to square root of n. So this gives you an algorithm which finds the size of the largest independent set in a planar graph in time, which is exponential in square root of n, which is much better than what you can do in general graphs. Modulo exponential time hypothesis in general graph, you cannot get better time complexity than exponential in the number of vertices. So, and of course, this choice of computing the largest independent set was kind of arbitrary. The same idea will work for many natural graph problems that are hard in general and presumably still hard for planar graphs, but a little bit easier. And also you see similar ideas also in design of some polynomial time algorithm and so on. So really, this property of having separators whose size is much smaller than linear is very useful in these algorithmic problems. And so people were interested in whether you can extend this result of Lipton and Tarja to other graph classes than just planar graphs. And it turns out that you can. There was some progression of better and better results. So Gilbert, Hutchinson, and Tarjan proved that this is true for graphs embedded in any fixed surface, not just plain, but let's say torus or anything like that. And then Alan, Seymour, and Thomas prove that this is also true for any proper minor closed graph classes. So if you let's say consider planar graphs, you know that planar graphs are just graphs that do not contain K5 or K33 as a minor, and it turns out that if you forbid any other minor, you will still get actually separators of size roughly squared of n. And there are a couple of other graph classes which have sublinear separators, some kind of geometric graph classes in bounded dimension. I will not go into details, but there are a couple of them. So kind of the idea is natural if you somehow embed something in three-dimensional space, then you can cut it somewhere here in the middle, and you will separate it into roughly the same size, and this size of your cut will now have something like n to the 2/3 vertices. Just considering the volume of the area that you are cutting around, pretty much. And yeah, there is one more kind of trivial, simple example, and that which is actually implied by this. Not good connection, and that is graphs of bounded treeways. And the reason why I'm saying that this kind of trivial case is because these are the graphs where you get the best bound on the size of the separators. Imaginable, you will get constant size separators. And, do I need to define what a treeway is, or does everyone know?
You might want to, because it's a little complicated.
Okay. So let me say what a treeway of a graph is. So, given some graph G, tree decomposition of your graph is a tree whose vertices are subsets of vertices of G. So to each vertex of tree, I am assigning some subset of vertices of my original graph. And now I want to have the following properties. I want that each edge of G, both ends of each edge of G are contained in one of these bags. And secondly, okay, let me call these subset bags. And if I have a look at which bags contain a particular vertex of my graph G, these bags should form a non-empty continuous subtree of my tree. So for every V in G, if I have a look at the set of vertices of the tree such that V is contained in their bags, this induces a connected subtree. So this is a little bit dense, and if you haven't seen this definition before, you probably will not be able to digest it now in 5 minutes. So let me just give you some rough and completely wrong idea of what treewise is. So imagine that your graph can be approximated by this tree T, such that you somehow explode each vertex of your tree into some subgraph of G. So imagine that your graph G somehow lives around this tree, and this tree sort of approximates its structure. And the important thing is that each of these bags forms a separator in your graph in the natural sense, in the sense that the vertices of your graph that live here are cut off from the vertices of your graph that live here by the vertices of the bag. And now, given the tree decomposition, the width of the decomposition is the maximum of the sizes of the bags. -1 for historical reasons, and the tree width is the minimum width over all possible decomposition. So, if your graph has tree width at most 10, this means that it has a tree decomposition in which each of the bags has size at most 11, and now each of these bags forms a separator in your graph, and if you somehow choose the separator which splits the tree evenly, you will get a separator which is balanced. So this shows that sort of shows that graphs of tree width at most 10 have balanced separators of order at most 11. Okay, so now we have some list of graph classes that have bounded size balanced separators. So what about some that don't? And now here the canonical example of a graph class that doesn't have small balanced separators are expanders. So we say that the graph G is expander if whenever you take a subset of its vertices and you have a look at the vertices outside of this set that have neighbors in S, there will be relatively a lot of them, at least a constant fraction of whatever we have in S. So G is an alpha expander for some real number alpha if for every subset of its vertices of size at most half, let's say the number of these neighbors vertices in the neighborhood of S is at least the alpha fraction of the number of vertices in S. And it is not very hard to prove that some alpha expanders exist. It's not even very hard to prove that there exists some that are regular, such that every vertex has degree precisely 3. For instance, if you take a random graph, it will with high probability be an expander for some value of alpha. And of course, if you take an alpha expander, it cannot have separators of sublinear size, because if you split your expander into parts A and B arbitrarily, you will now take let's say the smaller of the sides, let's say this one, because of this balance condition, this size will still have some linear number of vertices, something like 1/3 of n. I like here a little bit, but let's go with this. And so this means that the neighbors which necessarily appear in the separator will have size at least alpha times 1/3 of n. So the order of each such balanced separator will be necessarily linear. So so we now have some kind of lower bounds, some graph families, larger and larger, which do have balanced separators, and then we have some abstractions, which are these let's say expanders, which don't. And now the question is whether you can somehow characterize the graph families that have this property, that do have balanced separator of somehow some sublinear order. Now we might think whether this is actually a meaningful question, like whether somehow this property is not like fundamental or so simple that it cannot be reformulated in any other way. And if you work a little bit in this, you will get a feeling that it's not actually the case. Like let's say proving that planar graphs do have balanced separators is not hard, but it is not an easy exercise. Like it needs some work, and it exploits some structural properties of planar graphs. And the same thing seem to be here. Like all of these examples of the graph classes that we have here are some graph classes that do have some nice structure. And so the natural question is whether this is true in general, whether if you take any graph class with balanced separators, whether it will have some nice structural property. And well, okay, it's the way I stated this is obviously false, because you can take let's say the class of all graphs that consist of two components of the same size. So this has balanced separator of order 0, and it doesn't have any nice property at all. But you will immediately see where is the problem. I need to require this property to be hereditary. I need that not only I have balanced separators, but also that all my subgraphs have balanced separators. And this is again true in all these examples that I was showing so far. So that's nature symptoms. So this is somehow the main thing that I will be speaking about in this talk, and that I will not give you a complete answer to, but I will at least try to approach it somehow. So the question would be, if G is subgraph-closed class of graphs, okay, so it turns out that there is actually a nice condition that implies sublinear separators. But to describe this condition, I will need some more definitions. And the definitions that I will need are for a thing called bounded expansion. And so bounded expansion is sort of a misleading name, because it has pretty much nothing to do with the expanders, which I fortunately erased already. It's concept which was developed by Neschetřil and also Node Mendes, and it sort of aims to describe what it means for a graph class to be sparse. So of course, if I tell you that the graph class is sparse, then every mathematician imagines something different from it. Like Bernard would probably imagine that it has some quadratic number of edges, so because he wants to work with dense things, for that his Fleck algebras work. But that's not the case here. Like I will be really wanting to describe very sparse things that have linear number of edges. And also, other thing that I want to require from the sparse graph, that I cannot get this linear number of edges just by some kind of cheating. And what I mean by that, let's say I take any graph and subdivide each edge once. Now, the resulting graph will have average degree something like 4, or at most 4. So it has linear number of edges. But in this graph, it is in very simple way encoded all the complexity of the original graph. So even though it has linear number of edges, it's just by some kind of cheating. So I would like to avoid this, and I would like to somehow consider graphs only to be sparse, even if they remain sparse after, let's say, contracting some small radius species. So after undoing this subdivision operation. So this motivates the following definitions. So we say that the graph H is a depth R minor of G if I can obtain H from G by taking some vertex disjoint connected subgraphs of G of radius at most R, contracting each of these subgraphs to a single vertex, and removing all of the vertices and possibly some of the edges. So essentially, if H is obtained from G, from a subgraph of G, by contracting subgraphs of disjoint subgraphs of radius at most R. And by nabla R of G, I will denote the maximum average degree, or average edge density of a depth R minor of G. And given a class script G of graphs, I will also define nabla R for this graph, or for this class, as the supremum of nabla R G of the graphs in this class. And I will say that this class has bounded expansion if this number is finite for every R. So again, this is a little bit dense definition, so let me give you an example. Let's have a look at planar graphs. So what is nabla R of a planar graph? Well, here you take, and that's R minor of a planar graph, so this is sum minor of a planar graph, so it is again planar. You take its edge density, and well, we know that every planar graph has at most 3 times as many edges as it has vertices. So for every planar graph and for every R, this will be at most 3. So this shows that for the class of planar graphs, we have nabla R always at most 3, in particular finite, and so the class of planar graphs does have bounded expansion. Another example, if I take let's say graphs with maximum degree at most 3. Now, what will I get here? If I take depths are minor, so if I contract a subgraph of radius at most r in let's say 3 regular graph or graph of maximum degree 3, then each of the blobs that I am contracting has at most 3 to r vertices, and from each of these blobs that I'm contracting, I will also have at most something like roughly 3 to the r edges. So after this contraction, I will get graphs of maximum degree at most 3 to the r, or roughly something on that order, and so their edge density will again be something roughly on the order of 3 to the r. So here, this is, let's say, at most 3 to the r. So again, for every r, it is finite, but unlike the case of the planar graph, now this is growing with r. But this is perfect. Okay, this still satisfies the definition of bounded expansion. On the other hand, if you let's say take the class of cliques, well then just as nabla 0 of a clique, you will get just any subgraph of a clique, or in particular the cliques themselves, and cliques don't have bounded edge density, so this subprimum will be infinite. So the class of all cliques doesn't have bounded expansion, and similar, let's say, if you subdivided each edge once, it would start failing at the second step at nabla 1, and so on. So it sort of correctly captures this intuition that I was telling you about when I was defining the motivation for the bounded expansion. And so, what can we say about the expansion properties of these graph classes? So, anything that is closed on minors, or when you forbid a minor, every minor of your graph also forbid this minor. So it will still belong to the same class of graphs, and graphs with if you forbid a minor, it bounds the edge density by some constant. So here in all these cases where we have some forbidden minors, we will get nabla r bounded by being a constant or bounded by a constant. It is geometric graph classes it's sort of how depends what I mean by geometric graph class, but you can probably imagine that, let's say, in three-dimensional space, the neighborhood of a vertex grows, somehow polynomial with the distance. Let's say in three-dimensional space, if you go to dimension r, the surface of your thing will have size roughly r square, and so we will have, let's say, roughly r square vertices. So you can imagine that in this bounded dimension D, the nabla r would be maybe something like r to the dimension minus 1, but depending on what I precisely mean by this geometric graph classes. And on the other hand, if we take three regular expanders, we have seen here that, okay, they have max degree 3, so they still have bounded expansion by this exponential function, and it turns out that you cannot improve it much. You can improve the exponential a little bit, but not to anything sub-exponential. So they will have number r of order some constant to r. It turns out that it's not a coincidence that here the nablas are small and here they are bounded by some quickly growing function. There is a result by Nešetřil and Sonora Mendes. That tells you that if G has sub-exponential expansion, so with this nabla r is bounded by some sub-exponential function, then G also has sublinear separators. So it has balanced separators bounded by some function of n, which is sublinear. And of course, as you get here closer and closer to the exponential expansion, the bound that you will be getting on the sublinear function gets worse and worse. How much time do I have?
10 minutes.
10 minutes. Excellent. And the question that we are considering with Sergey is whether you can actually reverse this. At least of course for these hereditary graph families that are closed on subgraphs, because otherwise it doesn't make sense. So whether you can write here the equivalence. And it turns out actually that you cannot, because there are some graph classes that have very little bit sublinear separators, but still have exponential expansion. Like they may have separators of order like n over log n, and still have exponential expansion. But other than this small bump at the boundary, it actually turns out that you can. What we can prove is that if G has polynomial expansion, so the expansion function is bounded by some polynomial. This is if and only if there exists some epsilon which is greater than 0, such that G has balanced separators of order. N to the 1 minus epsilon at most. So this is actually in some sense even better than what we will be getting here, because if you consider, let's say, these algorithmic applications, if you have sublinear separators which are just very little sublinear, things sort of start to break apart. Some recursions don't work out the way you would like to. Like you get some extra logarithmic factors which kill your gains from the sublinear separators and things like that. So it's really better to work with separators of this size, which is bounded array from linear by some polynomial factor. And so it's nice that we can get this equivalence. Also, kind of thing that is nice here is that sort of nice, or also in some ways also unpleasant, is that actually it's pretty hard to find the right bounding function for the expansion of your class. Like we have now many tools how to prove that graph class has bounded expansion, but we have very few tools and very few ideas that would give you a sharp bound. Like we can let's say prove that the graph class has expansion bounded by a triple exponential in R, but we suspect that that its expansion is bounded by a polynomial. And so actually this is nice from the point of view that this gives you a way how to prove that the class of graphs has bounded expansion. And it turns out that actually, usually it is easier to prove that class of graphs has small separators than it's to actually prove something about expansion. So from this point of view, we didn't achieve all that much. Like we proved that class has bounded separators, sublinear separators, if and only if it has some other natural property, but the property that is actually harder to work with than what we started. So it's progress, but maybe in wrong direction. But anyway, it's I find it good at least to have this result from the point of view that it gives us some confirmation that we are not looking for something that isn't there. Like it gives us some confirmation that the classes of graphs defined by having sublinear separators also have some other non-trivial properties. So they probably do have some kind of structure that we could. So the next logical step would be that we would like here, still have something better. We would like ideally here to get some structural description, or in some, if I wanted to be the least ambitious, I would like to get some kind of certification for these properties. So I would like to be able to say that for every graph that has hereditarily separations of this order, I can find some kind of whatever substructure in this graph, or collection of subsets in this graph, or anything which would prove that this graph has this property. Let's say in sense that then I could run some polynomial algorithm which would tell you, yeah, now if you have this magic thing with these properties, it must imply standard by sublinear separator. And we don't have that. Like we have some ideas, but not much of them. Like it's okay. So the first step. The first thing that you could consider is consider some kind of variant on 3D composition. 3D compositions are nice because they give you plenty of separations of small size, and they also are nice from the hereditary point of view, because if your graph has nice 3D composition, then each subgraph, then this 3D composition will also be kind of nice for every subgraph of this graph. But unfortunately, it doesn't quite work here. Like by another result, it's with Sergey. We can prove that if G is hereditary, subgraph-closed, and it has separators, balance separators of order at most k, then 3-width of every graph in this class is at most 250 times k. So so if you have separators of this order, you can find a 3D composition where each back will have at most this size, and this 3D composition then certifies that every subgraph of this graph has a separator of roughly this form. But this is not quite what we want. Like imagine that you take some very small subgraph, which has much less than these n to the 1 minus 1 epsilon vertices. Then the 3D composition will tell you that, yeah, in this graph you have separation of order n to the 1 minus epsilon, but that's completely irrelevant for you, because now you are so small that this doesn't tell you anything. That you could just throw all the vertices in the separation and don't do that. So maybe we would like here to have some kind of iterated 3D composition, where you would have this 3D composition that would work for large subgraphs, and then some set of small 3D composition that would work for small subgraphs or something like that. We are still working on this. We don't quite know what actually we want to have there. And that's, I think, the good place to stop this talk.
So let's thank Zdeněk.
I do have a quick question. Is there are you able to describe the counterexample graphs for the de Mendes result?
You take let's say three-regular expander and subdivide each edge by log n vertices. Maybe could work. Like it will. Yeah, it will already have sublinear separators, because then if you remove the original vertices, they will form a small fraction and split it up, but it still have a large expansion.
Seems like cheating, right?
Yeah, it's cheating.
Subdividing always seems like cheating.
Yeah. So yeah, I sort of think that morally this implication back is also right, but yeah, there are some technical difficulties.
There may be too many to deal with.
What's the main method that you used for proving the equivalence?
Well, for this equivalence, to get these sublinear separators, this was actually known by a previous result by Colloquium, Rao and Smith, which have kind of a beautiful result which describes some condition for getting sublinear separators and so gives algorithm and so on. I will not go into the details. It takes some time to describe it. For this implication, we sort of you take here the graph obtained by contracting balls of small radius or subgraphs of small radius, and you would like to show that it has small average degree. And if it happened that it doesn't, that by contracting balls of radius r you have increased your average degree by more than some polynomial in R, you will be able to show that in that graph with large minimum degrees, you have some expander as a subgraph, and then this three regular expander as a subgraph. And now if you uncontract things, you will get some subcubic graph, which is obtained from an three regular expander by subdividing each edge at most 2r times or something. And you will argue that this cannot happen with the sublinear separators, which is, well, it cannot happen with sublinear separators of order which is significantly smaller than sublinear. Like, yeah, well, actually, if you take an expander and subdivides its three regular expander and subdivides its edge constant number of times, you will still have an expander which cannot have sublinear separators. Yeah, so this is the way we prove that contracting the balls cannot increase too much.
Other questions? Okay, so let's take Zdeněk again.